a moment to review similarity and how we would prove triangles are similar by AA, angle, angle, by side, side, side similarity, or side, angle, side. When we dilate something or we enlarge or reduce it, when we make a similar shape, I'll make a polygon here. What we do is we dilate around a certain spot. That's important to know. We have a point of dilation. So if I chose to dilate this from the center spot, not sure if it's going to let me. I guess it's not. So if I dilate outside the shape, it's always going to ask me for a scale factor. So the idea there, your scale factor is your proportion of growth or of shrinking. So if I want a scale factor of half, or I could put 0.5, it's going to make a triangle half the size. And it's going to be, when it shrinks, it's going to get closer to the point of dilation. When it grows or is an enlargement, the scale factor is bigger than 1. So if I put 2 or 3 or even 2.5, it's going to make a triangle 2.5 times bigger, and it'll grow away from the point of dilation. Now what I was trying to show is that you can make the point of dilation in the middle here, where I've just put point F. Then the triangle would shrink. Let's say if it was smaller, it might make a triangle like this. Let me connect it. And it would go around that center of dilation. I mean, it's not perfectly in the middle. Or it would grow around it and come outside, away from the center of dilation. So if the center or point of dilation is on or in the shape, it grows around the shape or inside the shape. If the point of dilation is on the corner, we could do that. When the point of dilation is on the shape, what we'll do is we'll see that it grows away or closer to that same point. So let me draw another triangle, and I'm going to dilate it on point A. So I'm going to dilate it from a point on the actual shape. I'll make it a quarter of the size, and we can see it shrunk down, but it stays stuck to point A. And when I grow around point A and make an enlargement, it also grows, but it is also fixed on that point A. So when a dilation grows on the shape, it dilates an enlargement or reduction and sticks to that point. So when things grow or shrink, as we're seeing here, we put in 3 or 2 or half, everything grows by that amount. So that's what's important to show when we're doing the triangle similarity properties. So the 3 properties we've learned are side, 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 angle, side similarity, and angle, angle similarity. I don't see my page marker pen. Oh, there it is. So with each of these that have sides, the side, 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 and side, angle, side, we're always going to have to check that the sides grew or shrunk, enlarged or reduced the same amount. So we'll have to make fractions. For angle, angle, we'll only need to check to find 2 or more angles. So let's go through some practice problems since we've already done these lessons and see if we understand how to approach it. So here we have 2 pairs of matching sides, so it can't be side, side, side. When you only have 2 sides, you always want to look for the angle. And in case you forgot, there's a vertical angle here. So that does have the side and angle and a side, side, angle, side. Now we need to test if the sides grew or shrunk by the same proportion. So it doesn't matter if we start with the smaller or bigger triangle when we're testing, but to test it, we're going to take 18 matches with 6, and the other 18 is the same. So you know most of the time after you've done these once or twice that if the numbers are exactly the same, of course, when you reduce them, they will be the same. So this is similar by side, angle, side similarity. And we would do a triangle similarity statement. U, V, W. So U is where the center is, where the vertical angles are, and then to V, then to W. So you could go U, F, G. A lot of times we want to spend time matching the sides exactly, the ones that go together, but when they're isosceles, it's not going to matter which direction we go. So number 2. Number 2, you see one angle and you might say, well, I don't have the other. So we have 2 things here. We can realize that these angles are corresponding. Therefore, the other ones would also be corresponding, so then it would be angle, angle. Okay, the other thing is if you look at those triangles and pull them apart, you had a small triangle and a bigger triangle. They shared the angle U. So that was the other angle we could have noticed. So this does have two angles, but they're just not expressed specifically. You have to, it's implied, you have to figure it out. So this would be by angle, angle, angle. If I go U to V to W, it would be U to BC. So we're matching the same order of the corresponding parts, the matching parts. Okay, number 3 looks like a side angle and a side angle and a side. So the smallest side here is 42. I'm going to match it with the smallest over here is 8. The bigger side here is 49 or 79. I'm going to match it with the bigger side here is 13. And I'm going to calculate whether those are the same. So let's take a calculator. 42 divided by 8. Oops, I got rid of the calculator. Is 5.25. 79 divided by 13 is different. So this is 5.25 and this was 6.0 something. So they're not similar, because they have to grow and shrink, enlarge or reduce by the same amount. So the fourth one, it looks like side, side, side. There's three sides, I'm sorry. So the biggest one, I want to match the biggest one here and see if they are going to have the same ratio. Oops. 36 over 14. The smallest one is, oops, that wasn't the biggest one. My mistake. The biggest one is 42. So the biggest 42 will go with 14. 42 will go with 14. We're going to test it to see if the smallest one, 30, goes with 10. And the last one was the purple one or blue one. 36 would go with 12. Those were the middle-sized numbers. Because if you have the middle number when you grow the shape, the other one that's the middle number will be the one that matches or corresponds. When you have the largest number and you shrink a shape, the largest number will continue to be the matching side. So I can reduce this as a fraction and see, is it 3 to 1? This one is 3 to 1, 3 to 1, 3 to 1. So typically a calculator is going to be quicker if you aren't good at reducing. So 42 divided by 14 is 3. 30 divided by 10 is 3. And then 36 divided by 12 is 3. So we really have 3 equals 3 equals 3. So we have proof that they grew or shrunk by either a scale of 3 times if it's looking at it as an enlargement, or really you could flip it upside down and say the small one is 1/3 the size. So sometimes people ask, can I work on it the opposite direction? Meaning, can I go pick the big one here and put that on top and match it with that? And it will. 14 goes with 42. The smallest one was 10, goes with 30. And then 12 goes with 36. If we reduce them with fractions, we get 1/3, 1/3, 1/3. So we're just changing our comparison. We're looking at how much did the small one shrink rather than how much did it grow compared to the other one. So if you use a calculator, you get an infinite decimal, 0.33333 for all of them. So those would be similar by side, side, side. And of course, we would then match the ones that go together. So, I'm not sure if this is going to let me move. Oh, it is. So, C is in between the biggest and smallest. That would be where K is actually. So the biggest is 42 and the smallest is 30. The biggest here is 14, the smallest is 10. So K would be in the same spot where C is. D is in between the biggest and the middle one. So the biggest and the middle one would be where L is. And of course the leftover one, M, has to go with E. So we can tell which ones go together to match the order of sides based on the location of the sides. So again, I know that K matches with angle C because angle C is between 42 and 30. Those are the biggest side and the smallest side. When I look at the other triangle, when I look at the biggest side is 14, the smallest side is 10, that would be the same position where K is. So angle C and angle K are going to be the ones that match. Remember, the order does matter when you grow or shrink. There will be certain sides that are the same. So if I take this side A and grow it and enlarge it, it might be called X now. They're the ones that go together. And we can tell by the side markings. So if 10 and 14 are the smallest and the biggest, and 42 and 30 are the smallest and biggest, we know that those are the same position. So if you have a question about that, ask on Monday. But this is how we begin to approach proving similar sides. We're going to find angle, angle, side, angle, side, and we're going to test the sides, or side, side, side similarity, and we test the sides to see if they all match and grow and shrink together with the same amount. So hopefully this helps. Please ask questions in class.